Okay, we want to get a handle on the idea of arc length, or arc distance. Okay. If our r of t, our position function, is x of ti plus y of tj plus z of tk, where t is a parameter, so this is a parametric representation in terms of t of the vector that traces out our path, then the velocity vector, if we interpret t as time, our velocity vector would be dr dt. And dr dt, of course, is just a derivative, x prime plus y prime plus z prime times the I, j, and k. And that's straightforward. Okay? Now, if you multiply speed by time increment, you get the distance increment. Okay? In other words, in a short time t, how far do you move? Well, you multiply that short time interval by your speed, and that's how far you move. What's the speed function here? Well, the speed is the absolute value of the velocity. It's the magnitude of the velocity. I said absolute value, it should be magnitude. And I probably should have used a set of absolute value signs with attitude. Magnitude of v of t. And that's just clearly square root of x prime squared plus y prime squared plus z prime squared. Figure in there. And I wrote that as dx dt squared plus dy dt squared plus dz dt squared. Now that would be the, okay, that's the speed. If you integrate the speed with respect to time, you get your distance. Because on every little increment of time, you're multiplying speed by how much time has elapsed. So you're accumulating distances when you do this. So the integral from t equals a to t equals b of your speed with respect to t is your distance. Okay? Now, I actually interpret that at the end of this, but you see where we're going with it. So this equals this, and this equals the integral of your distance increment. Okay? ds is your distance increment. So s of t is a distance, what, no, never mind. Okay, ds is your distance increment. So this integral becomes the integral of ds. I should have written what ds is. ds equals the square root of x prime squared plus y prime squared plus z prime squared, naturally you can't read that, times dt, equals the magnitude of v dt, if you use the velocity and position. Well, if you use the, if you use the idea that t does represent time. It doesn't have to. Okay, you would still get what's going to be our arc length interval, whatever your parameter t stands for. You just do the same operations. Okay, so we say this is the integral of ds, integral of our distance increment from t equals a to t equals b. So we're going to say that that equals what? Well, the integral of dx is just, the antiderivative of dx is just x. Okay? The antiderivative of x of t with respect to t is just, did I say that? No. Antiderivative of dx of t with respect to t is just x of t, and so forth. So the integral of this is just s of t evaluated between a and b. Okay, and this defines your distance function. Okay, that's s of b minus s of a. S of t then would be interpreted as the distance traveled since t equals 0. So there is your result. This is your arc distance. It's basically a velocity times time integral. And we define S of t then, since it's a distance traveled since t equals 0, we define S of t to be the integral from 0 to t of the magnitude of your velocity. In this case now I'm writing it as the magnitude of r prime, okay? And instead of t I'm using tau for the variable of integration, since I don't want to confuse it with t. Okay, so S of t is the integral from 0 to t of magnitude of r prime of tau d tau, and that's the integral from 0 to t of ds, where again, well, S is your S of, where ds is equal to the square root of r prime of tau d tau. Okay. Again, this is your arc length increment. Now I wrote your arc length increment as this, okay? And down here I wrote it this way, but of course the magnitude, and I've got the square root when I should have the magnitude. I really got to find a way to get around doing so much of that. Okay, I mean, had it here. Maybe if I'd have used the absolute value sign with attitude, I wouldn't have written a square root here. I mean, it's a square root, but it's the magnitude of r prime of t. And we see that the magnitude of r prime of tau, or r prime, magnitude of r prime of t would be this. Magnitude of r prime of tau, same thing, but with the other variable. Okay, so there's our distance increment. Here's our distance increment. And S of t is our arc distance function, the thing that you get when you integrate this. Okay, well, we'll talk about what that might mean. And an important distinction, the distinction between your R function, which is a position function, and your S of t function, which is a distance along the path function.